Hello students, I am Dr. N.S. Hungund, Head Department of Mathematics, Shri Haugiswami Mahavidyalaya, Udgir. Today I am going to consider group theory. Group theory is designed for the students of BSc second year, third semester of Swami Ramananda Tirtha Marathwada University, Nanded. Group theory consists of introduction, mappings and integers, groups, subgroups, normal and quotient groups, homomorphism and isomorphism, and automorphism. So to begin with, let us consider the introduction part for the students of BSc second year. Well, students, tell me, what is a set? Yes, set is a well-defined collection of objects and is denoted by capital letters A, B, C, X, Y, Z, etc. The objects in the set are called elements or members of the set and are always denoted by small letters A, B, C. Here, what do you mean by well-defined collection? Suppose your mom told you to bring flowers. So what will you do? You bring only flowers or you bring flowers along with the apple? No. You bring only flowers. That means you are bringing the objects following the same property. That is, you are collecting the objects of following the same property, and that is called the collection, which is well defined. So now if S is any set, then element of set S is denoted by A belonging to S. Now there are many types of sets. In those, finite and infinite sets. A set consisting of finite number of elements is called a finite set, and that consisting of infinite number of elements is called an infinite set. Empty set, sometimes it is also known as null set, void set, etc. A set containing no element is called an empty set and it is denoted by phi. The most important set in set theory is universal set. So what is universal set? Universal set is nothing but a particular set which contains all objects or elements likely to be considered. And this universal set is denoted by capital U. And sometimes this universal set is also referred as frame of reference. Subset. The set A is called subset of set S if every element of A is also there in an element of S. So A is contained in S or S contains A, and we write it as A subset of S. Equality of two sets. If A is subset of B and B is subset of A, then we call it as A is equal to B. Proper subset. Suppose A is a subset of S, but A is not subset of S, or A is not equal to S, then we call it as a proper subset of S. Note, always A is a subset of itself and empty set is subset of A always. These are called axioms. Axioms, that is granted results. Now let us see some of the properties of set theory. Union. The union of two sets A and B is nothing but the set containing elements of A or B or both A and B and is denoted by A union B. Now let us consider the properties of union in brief. If A and B are two subsets of a set S, then A union A is equal to A. A is subset of A union B and B is subset of A union B. A union B is equal to B union A, that is commutative property. A union B union C is equal to A union B union C, that is associative property. If B is subset of A, then A union B is equal to A. Intersection. The intersection of two sets A and B is nothing but the set containing elements which are common to both A and B, and it is denoted by A intersection B. Properties again of intersection are: if A and B are two subsets of a set S, then A intersection A is A intersection B and is a subset of both A and B. A intersection B is equal to B intersection A, that is commutative property for intersection. A intersection B intersection C is equal to A intersection B intersection C, that is for associative property for intersection. If B is subset of A, then A intersection B is always equal to B. Complement. The complement of a set A is nothing but the set containing elements of S but not of A. That is, set of elements belonging to S but not of A. That it is denoted by A complement or S minus A. Properties of complement. If A and B are two subsets of set S, then complement of a set A is A. A union A complement is whole of the set S. A intersection A complement is empty set. A union B complement is equal to A complement intersection B complement, and A intersection B complement is equal to A complement union B complement. These two are known as De Morgan's laws. If A, B and C are given subsets of S, then A union B intersection C is equal to A intersection C union B intersection C. In the same way, A intersection B union C is equal to A union C intersection B union C. And these two are known as distributive properties. Cartesian product of two sets. The Cartesian product of two sets A and B is the set of all ordered pairs AB, where the first component A belongs to the first set A and the second component B is belonging to the second set B. And this Cartesian product is denoted by A cross B. So whenever A1, B1 is an ordered pair, similarly, A2, B2 is also ordered pair and they are said to be equal if they are equal component wise. In general, A cross B is not equal to B cross A, and this is illustrated with the example: if A is equal to set containing A and B and B is equal to set containing 1, 2, 3, then we have calculated A cross B as well as B cross A. The very first element, the ordered pair A1, is always not equal to ordered pair 1A of B cross A. So therefore, in general, A cross B is not equal to B cross A. Now, the set A cross A, that is the Cartesian product of set A with itself, is denoted by A cross A, and it is given by the set of all ordered pairs which are elements of A. Now, coming to the very important thing, that is a relation. Any subset R of A cross A is called a relation on A. And if A comma B belongs to R, then we write it as A related to B. There are three types of relations: reflexive, symmetric, transitive. Reflexive. A relation R is reflexive if A is related to A for all A belonging to A. That is, every element is related to itself. Symmetric. A relation R is said to be symmetric if A related to B implies B is also related to A. Third, transitive. A relation R is said to be transitive if A is related to B and B is related to C, then A is related to C for A, B, C belonging to A. Equivalence relation. If the relation R is reflexive, symmetric and transitive, then it is called as an equivalence relation on A and it is denoted by the symbol called nabla. If S is the set of integers, then for A, B belonging to S, let us define A related to B if A minus B is an even integer. Then we easily prove that nabla, that is the relation, is an equivalence relation on set S. Equivalence class. So whenever there is an equivalence relation on a set S, then we can define equivalence class. So the equivalence class of an element A belonging to S is nothing but the set containing all those elements of S which are equivalently related to A, and this is denoted by equivalence class of A. For example, equivalence class of 0 is set of all elements in the set of integers which are equivalently related to 0. That is, x minus 0 is equal to 2m, where m is any integer. Next, if you consider x is equal to x minus 0 equal to 2m, therefore x is equal to 2m, means all the multiples of 2 you have to consider, they form the equivalence class of 0. Similarly, if you consider equivalence class of 1, then equivalence class of 1 is given by x is equal to 2m plus 1, means all odd integers are to be considered, and this is nothing but the equivalence class of 1. Theorem. An equivalence relation always induces a partition on set S into mutually disjoint equivalence classes whose union is again S. For example, if S is set of integers and n is any fixed positive integer, let us define a relation A with B if A minus B is a multiple of n. For A, B belonging to S, then we can easily prove that this relation nabla is an equivalence relation on S. And here the equivalence class of A is considered as set of all x belonging to S such that x is equivalently related to A. That means x minus A is equal to multiple of n, and this gives you the equivalence classes from, if you consider from 0 to, so equivalence class of 0, equivalence class of 1 and so on up to equivalence class of n minus 1. And next, if you consider equivalence class of n, it is equivalent to equivalence class of 0, equivalence class of n plus 1 is equivalent to class of 1 and so on. And here we observe that the given thing is considered. Thank you.